Hello again, guys. Good morning. We're going to keep going here with vector dynamics. Well, this is chapter 2. I know some of you haven't written the chapter 1 test yet. That's okay. It's coming, I'm sure, for all of you. But we need to keep moving, so we're going to get started here with vectors, or vector dynamics, rather. This will look a lot like the grade 11 version of dynamics did, but we're adding, as always, vectors to it. So a bunch of this should be review to start, and we'll add the new stuff kind of at the end. So this would be always a discussion that we have, but you're not here, so I'm just going to keep going. Now, a force is a push or a pull. It is a vector because it has a magnitude measured in units of newtons. Forces are measured in newtons. It's not always just a push or a pull. Sometimes an object creates a field that another object interacts with, and that field will create a force on an object. But for the time being, this will be sufficient. So we've got some descriptions here. An Earth pulling on all objects downwards towards the planet's center. Well, that is obviously gravity. And the symbol is Fg. We're going to have a couple different formulas, or F sub G, we have a couple different formulas for that. Microscopic hills and valleys between an object and the surface, interlocking and preventing or impeding sliding. This is friction. Typically, the symbol is F sub little f. And then we've got a surface pushing up on objects, the parent weight of an object. We call this the normal force. I want to make some notes here. The symbol for this is F sub big N. Now, this idea that it pushes up on objects is not totally true. It's not necessarily up. It is perpendicular to the surface. And that is a note you should certainly make in here. One of the things that I've talked to a lot of Physics 11 students about is that, oh yes, normal force is up. It's up, it's up, it's up, it's up. And that's not true. It acts at a right angle to the surface. So if your surface is not flat, the normal force is not going to be up. For example, if I had something that looks like this, if that's my surface, then Fn is going to look like this. If this is my surface, then of course Fn is going to be up because it's perpendicular to my surface. Let's keep going. A force from a stretched string doesn't have to be a string, could be a cable, could be a rope. It is constant throughout that object. This force we typically call tension. And that is F sub big T. Sometimes it's just called big T. But big T has other meanings that we're going to get into, so don't let that confuse you. Then there's a contact force, usually from an external agent, usually a person. Doesn't have to be a person. But this contact force from an external agent, we typically call that an applied force. We'll call that FA. And then the force of resistance from the air opposite to the direction of motion, we call this drag. And that's it'll be called either F sub air or it'll be called F sub drag. We typically write that out. And then this is not a force, but it is the vector sum resultant of all the forces acting on an object. This is net force. And we call that F sub net. Okay. So these are all these are typically what we use in Physics 11. A couple notes here. This is a very general term. Anything can be an applied force if you don't necessarily know what it's where it's coming from, or if it's coming outside the object. Anything can be labeled as an applied force. It's important to recognize that there's a lot of freedom on how you label forces. So how you label a force depends on your perspective. I'll show you what I mean as we do some of these questions here. Note that I want to make here, we're going to start talking about gravity here. There's a distinction here that we're going to make between kinematics and dynamics. Kinematics is the chapter we just came from. Dynamics is where we're going. We're going to differentiate here some gravity rules. Now, in kinematics, the acceleration due to gravity equals negative 9.8 meters per second squared close to Earth's surface. This value changes the further you get from Earth's surface. In dynamics, we don't call it an acceleration. We say that little g is 9.8 newtons per kilogram. So the units are fundamentally different. And this little g is gravitational field strength. Near the surface of Earth. So when we look at dynamics, we think about gravity as a field. You can't touch it, you can't necessarily see it, but we always feel its effects on us. And that's because every massive object creates a field around it. Look at this in more detail later, but every object creates a field around it of gravitational strength, and every object has a different strength of a gravitational field. And the Earth's gravitational field causes an acceleration, and we deal with, in kinematics, we talk about it as an acceleration of negative 9.8 meters per second squared. In dynamics, we say, well, the gravitational field strength is 9.8 newtons per kilogram. So they're related to each other. Certainly, the gravitational field strength causes an acceleration, but it's important to be able to talk about them and understand them differently. So force, what we're getting into this now here, you have some experience with is the force of gravity between you and the Earth. This force is also known as the weight, or as your weight, and it's measured in newtons. This is metric. Pounds is the old imperial units of measure. So newtons in pounds are a measurement of weight. Weight in newtons. So this is different than mass. Make a distinction here. And in the old imperial units, which a lot of you probably know your weight in imperial, the weight is in pounds. Okay, so there's a distinction between weight and mass. We'll get there. Right now, actually, force of gravity is not the same thing as mass, although they are related. Mass, let's put this in here, not the same thing as mass. Mass is the amount of matter in an object measured in kilograms. To relate mass to force, we need to know the number of newtons of force per kilogram of matter in the gravitational field. This quantity is known as gravitational field strength. Near the Earth's surface, the gravity field has a strength of 9.8 newtons per kilogram, and it gets smaller as we move away from the Earth's surface. For example, the moon's gravitational field is about 1.6 newtons per kilogram. Just a fun little fact. So the force of gravity, your weight, and its relation to your mass is given to you by this formula here. You should have seen this. Oh, sorry. I did this up. Sorry, guys. Here. Whoa! This thing's down there. Okay, so you'll need a sec to write some stuff down here. Where was I here? Yeah, weight is measured in newtons. Metric units for mass are kilograms. Imperial is pounds. Fg equals mg is a formula that you should be familiar with from Physics 11. Fg there is your weight measured in newtons. It's also called the force of gravity. Those are equivalent. M there is your mass measured in kilograms, and little g is gravitational field strength. Oh, so let's do some stuff like this. Sorry, I need to move some stuff around here. There we go. Flip page. Just some simple examples relating these things together. Again, you should have seen this last year in Physics 11. On the Earth, I want to find the weight of a 10-kilogram object. This is mass. To find its weight, Fg equals mg. So the force of gravity, also known as the mass, on Earth is going to be 10 times 9.8. So an object is going to have a weight of 98 newtons. That same object is going to have a different weight on the moon. On the moon, little g is equal to 1.6 newtons per kilogram. So when we run this through, our mass is going to be 10 times 1.6. So that same object is going to have a mass of 16 newtons. Okay, it's important to recognize here that this is the same object. Same object, the same 10-kilogram object, interacting with different gravity fields. Okay. Now, if the force of gravity acts on an object, then what happens to the object? Does it remain at rest? Does it move at constant speed? Does it accelerate in the direction of the force? Can you think of examples where this happens? Well, I've got objects sitting on my desk. They're not moving, but gravity's interacting with them, so that's true. Can a force of gravity acting on an object, can that object also move at constant speed? Yeah, you can walk perpendicular to the force of gravity. You can have a constant speed perpendicular to the force of gravity. Gravity is still acting. Can it accelerate in the direction of the force? Yeah, it can push you off a building, you will fall. Gravity is pulling you down, you're accelerating towards the ground, so it works. So all three of these are an option, so D is your best answer, all of the above. Depends on what else the object is interacting with. It's not just gravity. Newton's second law says this. If we have balanced forces, then objects at rest remain at rest, and objects in motion remain in motion. So the math looks like this. If F net equals 0, so the sum of the forces is 0. This is what balanced forces look like. Then the acceleration equals 0. The object will not be accelerating. The object will remain at rest, or if it's in motion, it will remain in motion. There is no acceleration on it. If we have unbalanced forces, then the object accelerates in the direction of the net force. That is given to us by this formula here, F net equals ma, which you've seen before. F net is measured in newtons. Mass is measured in kilograms. Acceleration is measured in meters per second squared, which gives us a handy little relationship. It gives us that a newton is equal to a kilogram meter per second squared, which also tells us that acceleration can be measured as a newton per kilogram, which is how we relate our gravitational field strength and our acceleration together. They're the same thing. The strength of your gravitational field is going to be equal to the acceleration created by that gravitational field, and that's a really cool result. Next example. We want to find the unbalanced slash net force slash resultant force, whatever, in each case, and we want to include the direction. So if I've got one force acting on this guy here, this should all be really easy review. F net equals 2 newtons. I hat, we're going to use I hats and J hats. F net here is 1.5 plus 2.2. These guys are both acting down. This is negative 3.7 J hat. It's down, so it's negative. This guy here, it's my F net. I've got a 3 up and a 2 down, so that's going to be 1 newton. 3 is up and 2 is down, so that's going to be positive J hat. I've got 8 to the right, 3 to the left, so this is going to be F net is going to be 7 plus 1 minus 3 is going to equal 5 newtons in the positive I hat direction. My F net here, that 2 newton and that 2 newton are going to cancel out. I've got 12. Sorry, I'm going to have negative 12 plus 5. That's going to equal negative 7 newtons I hat. And we know that if y is greater than x, y is down, x is upwards. We know that F net is going to equal y minus x newtons J hat. And we know it's going to be negative. So actually, I can write it like this. The absolute value of y minus x, and then I can make it negative to explicitly say that the direction here is negative J hat. That's how I'd write that. Again, that should all be review. Flip the page. I don't know how Mr. Morrison showed you. Typically, he will, him and I are very similar in our expectations here, I think. To solve force problems, we have the expectations that you draw a free body diagram. How his and mine look are typically going to be, well, could be a little bit different, but typically should be very similar. So to solve these problems, you should always draw a free body diagram. The free body diagram labels all of your forces. Draw one arrow for each force, not F net. We do not include F net on a free body diagram that acts on the object. We want to label all your arrows. What are the forces? We want to put a tail on the arrow at the center of the object. We measure everything from the center of mass. So we shouldn't say at the center of the object, because the center of mass is not always going to be at the center of the object. So let's think of it that way instead. Instead of labeling the forces from there, we want to label them typically from the center of mass. Though I'm going to get sloppy. I'm not going to draw everything to the center. I'll draw it to the edge of the object. That's typically how I will do it. The book here suggests that acceleration and velocity vectors should be drawn differently from force vectors using, for instance, a squiggly line like the one shown. This is not super urgent. As long as you label things properly. So this should be a review of a question you would have looked at last year. You've got a 2,000 Newton rock accelerating upwards at 3 meters per second squared. Draw a free body diagram, compare the forces that act on the object, write in a force equation, find the tension in the cable. Let's go through these steps. So I'm just going to add my forces directly to the image that we've got drawn here. What forces are acting on my object? Well, I've got tension upwards. See, and I'm not going directly to the center of mass of the object because there's writing there. I'm just going to go along where the rope is. So we've got F tension. What else we got going on here? We've got the mass of the rock interacting with gravity, creating an FG downwards. Those are all the forces acting on my object. I know that I've got an upwards acceleration, 3 meters per second squared. And actually what I should be doing is I should be including arrows on the top of all of these guys because these guys are vectors. Don't get sloppy with your work. Oh, and I'm going to go back up here. We can stop being quite as concerned with the idea of negative I hats and j hats at this point, because sometimes it's going to become useful to have alternative directions for positive and negative. Okay? So I've got a force of tension acting upwards, I've got Fg acting downwards, I've got an acceleration acting upwards. The other thing we've got to add onto this diagram is which direction we want to be positive. So it actually makes sense. It doesn't matter which way we do it, but in this particular question, I'm going to say that up is positive here. So we can fill out a few more things here. We know that Fg, there's some, we know the weight of the rock, 2,000 newtons. It's cool. So that's everything we know. We want to, ultimately what we want to do here though is find the tension in the cable. So this is a dynamics problem, so we're going to start here every time. F net equals MA. Now we need a few things here. We need to know what the mass of the object is. All we have is the weight. So we can go back and we can convert the weight into a mass. We know that Fg equals mg, 2,000 is going to equal m times 9.8. So the mass of my object is going to be 204.08 kilograms. Sorry. Net forces is the sum of my forces. So this is just going to be tension. Sorry, that's not how I want to write that. Ft, force of tension. We said that up was positive, so this is going to be minus Fg. That's going to equal Ma, and we can start putting values in here. So Ft minus 2,000 is going to equal 204.08 times 3. So my force of tension is going to equal, this is going to be 612.24. Plus 2,000 is going to give me a tension force equal to 2,612.24 newtons. And that's acting up. So we can jump back and forth between these ideas of I hats and j hats and the directions we've got in the problem relatively easily. That's a question you would have done in Physics 11. You guys should be comfortable with that. Flip the page. Is it true to say that the rock in the previous example is moving upwards, then the string tension has to be greater than the weight of the rock? We would have a discussion about this if you were here, but that is false. Okay? Tension, force of tension, could be equal to Fg. That would mean acceleration is equal to 0. What that implies is it's either constant v So v is equal to 0, but v could also be greater than 0, and v could be less than 0. We just know v is constant. So our object, if the object's moving upwards, it could be either one of these. Well, sorry. If it's moving upwards, then it has to be this one. But my acceleration could be 0, which tells me that my tension and my gravity are equal. You can move an object without it accelerating. Okay. You could also have force of tension is greater than force of gravity. What that means is that the acceleration would be greater than 0, so this object would be accelerating. But you could also have it such that the force of tension is less than Fg. That tells you that the acceleration is less than 0. It's accelerating down. These are the different scenarios you could have here. But if the rock is moving upwards, it's important to recognize here that you could have either force of tension equals force of gravity, which would give you a constant velocity upwards, or you could have it bigger. So no, it's false. The tension doesn't have to be bigger than the weight. For a rock moving upwards, is it ever possible for the core tension to be less than the weight of the rock? Is it ever possible? When it says things like that, you got to be very careful here. Could you conceive of a scenario that the tension in the cord is less than the weight of the rock for a rock moving upwards? I could. Whether or not you can is debatable, but yes, it is possible. What you could have here is you could have this situation. You've got a rock, tension is upwards, force of gravity is downwards. It's got a velocity that way. It's got an acceleration that way, and tension is less than Fg. What that means is this: you've got a rock on a cord, but you've thrown it upwards. So the tension is less. There still could be a little bit of tension on there, but the tension is less than Fg. You've got an object that's kind of in free fall. Okay, so yeah, could you conceive of a scenario where this happens? I just did. So you gotta be really careful when it says things like, is it ever possible? Be very, very hesitant to say no until you've ruled out all sorts of ridiculous scenarios. There's a technical comment. If the mass of example 5 is accelerating downwards, we have two choices. We could use a sign convention from the previous unit. We can use up, right, positive, down, left, right. Or sorry, up and right being positive, down and left being negative. For the rock, we would then say that, you know, we have this scenario. We could also, though, take the direction of the acceleration or the larger forces as positive. So this is what I said before. You can choose now which direction you want to be positive. And I know Morrison does this. So if you had physics with him, you've seen this before. Approach A, using I-hats and J-hats, works really, really well in one-dimensional problems. But as soon as you get to two-dimensional or even three-dimensional problems, it's not going to work very well. So what we're going to have to do is we're going to start using this, deciding which way we want to call positive ourselves, instead of relying on the I-hats and J-hats when we start using multi-dimensional problems. Okay, flip the page. Give you some exercises, not a lot, just to get you reviewing this stuff. I want you guys to look at I guess there's 6 questions here. I want you to do 2, 4, 5, 7, 9, and 10. And that's it for this lesson. Hopefully this is review. If you're struggling with this at all, let me know. Comments, questions, concerns are always welcome. Good luck.